Hello students, today we are going to see about some more topics that is given in Tamil Nadu State Board syllabus, class 11. It has two chapters, fundamental basics of organic chemistry and basic principles of organic chemistry. So let us see first of all the 3D representation of organic molecules. Actually, it is represented, the organic compound, the sp3 hybridized organic compound usually represented in tetrahedral manner. That already we have discussed in our previous video. That link I will attach with the description. Then later on, the three-dimensional representation of tetrahedral molecule that can also be represented three more different forms of formula. One is called Fisher projection formula and Saha's projection formula, then Newman projection formula. Let us see Fisher projection formula. This Fisher projection formula actually represents a three-dimensional molecule into its two-dimensional way. Let us take an example of tartaric acid. Tartaric acid formula CHOH COOH CHOH COOH. See, the bond should always between the carbon atoms, so we have to make a proper notation of the bond. In tartaric acid, you may find two chiral carbon. What is chiral carbon? The carbon with four different valency. How can you identify the four different valency? See, one hydrogen, one OH, one COOH, and the other group is the entire part of CHOH, COOH. Similarly, take this carbon, it has H, OH, COOH, and the first carbon becomes the fourth substituent. So, the carbon with the four different valency can make asymmetric carbon atom, and it is also said to be chiral carbon. In detail, we will discuss about this one in optical isomerism. So, this molecule that can be represented like COHH or CHOH. This is nothing but the two different way of representing the data groups of different substituents of carbon. And you find over here, see, the groups which are given in wedge-shaped bond, that represents the groups are lying in a plane. That means the horizontal substituents that lie along the plane. And you may find the vertical four carbon atom COOH, COOH. All the carbon atoms are bonded with dashed line. The dashed line that makes the carbon atoms are at the vertical position. So, the vertical position, you can't able to see the group, you can view the molecule from their horizontal substituents. This is what the representation of Fisher projection formula. The next one, Saha's projection. This is a carbon-carbon axis is just represented in a tilted way. Actually, we will make carbon with their group Cl, H, CH3, NH2, H, CH3. We can represent such a way. So, you can find the carbon is exactly perpendicular to each other. So, this carbon-carbon bond, when it is represented in a slight tilted manner, you can find the carbon-carbon bond in its where. So, this carbon, it has three different groups CH3, HCl. And it's another carbon that has NH2, CH3 and hydrogen, this hydrogen. And you may find the two wedge-shaped formula in which methyl group is present, and the hydrogen of the two other atom that just given in dashed line. That makes they are just behind the first carbon and the second carbon. Then you may have carbon NH2, carbon Cl, this alone lying on a plane. So, this portion of the molecule, you can able to find it on a plane. CH3 and hydrogen of the other two groups in both the carbon that behaves just out of the plane. So, how it is given? You may find you can view the carbon from this way. So this is called a front carbon, through which only the observer can view the molecule. So when you view the molecule, you can't able to find the rear carbon, because the rear carbon is exactly behind the front carbon. So in such cases, you may find out what about their structure and how they are arranged, and this will be discussed in detail in hydrocarbon chapter, because these are the part of conformational analysis. Okay. Next thing, both the carbon atoms are sp3 hybridized. So one of the sp3 hybridized carbon that makes front portion, and the other sp3 hybridized carbon that becomes the rear carbon. Here the molecule that is taken for explanation is nothing but 3-chlorobutane 2-amine. So in this case, we can find the relative position of the molecules, but in Fischer projection formula, you can't able to find the relative position of the molecule. That means the group with respect to one another, we can explain where they are present. But here you can explain how they are present. See, with respect to methyl, the other methyl I have. And the chlorine, with respect to the chlorine, the other NH2 group is also lying on a plane. Such a way you can't able to explain about Fischer projection formula, because it is represented in two-dimensional way. The next one is Newman projection formula. Newman and Sahas, they are represented in a similar pattern. That means front carbon you can view, but the rear carbon you cannot view. So such a way of representation is just modified into a circle. See, when you keep two rings one behind the other, you can find the front ring, you can't able to find the back ring. That is what you have to observe. These are composed of two circles. One circle, it is in front of you, the other circle is just behind it. So how the groups of these carbon atoms is represented? See that I have an origin and I have a circle. The circle to which the groups are represented with shorter bond, and the origin with the groups, it is represented with longer bond. So through which the origin you can view the molecule, and the groups which are on the circumference of the circle, it is farther away from the viewer, that is the behind the one. So in which all the three substituents, they are represented at an angle of 120 degree. This can also be explained in detail in hydrocarbon chapter, and it is called fully staggered form. That and all we will discuss in hydrocarbon chapter. We are going to find tautomerism. Tautomerism is one of the part of isomerism. It is given in Samachir Kalvi syllabus. So what is tautomerism? Tautomerism is due to the formation of the difference in position of hydrogen from one of the carbon to other carbon, or from one of the substituent to another substituent, where hydrogen moves, that gives rise to tautomerism. This tautomerism, we have two different one is diode system, the other one is triode system. Besides that, we have one more form of tautomerism, that is called nitroacid tautomerism. So what is called diode system? See, in this diode system you have the group of cyanide, to which carbon is attached with hydrogen. But in the another case, you may find the hydrogen is attached with nitrogen. So when hydrogen is oscillating among the two atoms, that is said to be diode system. Hydrogen that oscillates either with the carbon or with the nitrogen, it gets occupied, that is called the oscillation of hydrogen. So such a way this is explained for diode system, and the molecule is actually cyanide structure. This is cyanide structure and it is isocyanide structure. Then what is triode system? Okay, when the previous case hydrogen oscillates among the two atoms, triode means 3. So here the hydrogen will oscillate among 3 atoms. Let us take an example of acetone. This is acetone. In IUPAC name it is propanone. Formula of acetone is CH3COCH3. I have 3 carbon atom. I can represent carbon atom 1, 2, 3. So from the first carbon or from the third carbon, the hydrogen that can oscillate among the 3 carbon atom. So let us take on this one. I am going to take the hydrogen from first carbon. It just gets moving towards the second carbon, and in turn oxygen withdraw its pi bond. A carbon oxygen, it has one pi bond and other one is sigma bond. So the pi bond of oxygen that gets, that means the hydrogen that moves from CH3 group to the CO group, that is called the carbonyl group, and hence you are finding the CH3 into CH2 as one of the hydrogen moves towards oxygen, and the CO group, it turns into COH because one of the hydrogen moved from CH2 to the second carbon CO, so that is COH group. In this case, the group is keto. CO group is a keto group. In this case, it has alcohol group. Along with alcohol, it has a double bond. That's why the name is given enol. En for double bond, OL for alcohol. So this is enol. So such triad system, by taking an example of acetone, we can say it is keto-enol tautomerism. The next one, nitroacid tautomerism, for which we are taking nitrous acid, HNO2. The compound is nitrous acid. In this nitrous acid, we may find a nitro form of nitrous acid. That means we are writing the compound as HN double bond O. This is nitrous acid structure. But at the same time, the hydrogen that can oscillate towards the other oxygen. By that time, we will get this molecule, that is nitrite structure. So how we can do? The hydrogen that moves to oxygen, so we may find NOH double bond O. This is called acid form. So the nitrite, and it forms nitro form. This is known as acid form. This is acid form. This is nitro form. Why it is called acid form? See, the OH group to which the hydrogen attached has acidic property. So this is called acid form of nitrous acid, and this is nitro form of nitrous acid. And this will be explained once again in your nitro compound structure. Okay. Then the last form of isomerism is ring chain isomerism. We know the alkenes and the cycloalkanes have same general formula. What is that? CnH2n. So let us take C3H6. C3H6 I can represent in the way of an unsaturated alkene, propene, CH3, CH double bond, CH2 is propene. The same 3 carbon with the 6 hydrogen can also be represented in its cyclic form. So here the name it gives cyclopropane. So same molecular formula, but giving rise to 2 different structures. Such structures, one is the open chain structure, the other one is cyclic structure. So it is called ring chain isomerism. Similarly, if I have butane, so it has a 4-membered ring. That 4-membered ring can even be converted into its 3-membered ring. So in which one of the carbon is taken as the substituent, methyl substituent. So this is a 3-membered ring. This is a 4-membered ring. So the size of the ring can also be altered by taking the substituent of the previous one. Okay. So these are what the different forms of isomerism. Under stereoisomerism, let us discuss about geometrical isomerism and optical isomerism, because in Samachir Kalvi it is given in detailed manner. So geometrical isomerism, it has 2 different forms. One is cis-trans form, the other one is syn-anti form. Okay, what kind of molecules can exhibit geometrical isomerism? Before that, already we have discussed about stereoisomerism in the previous video. In stereoisomerism is nothing but the spatial arrangement of groups with respect to one another in a 3-dimensional way. So geometrical isomerism, let us discuss about what is cis-trans isomerism. So let us take an example of but2ene, 1, 2, 3, 4. The second position has double bond, 4 carbon it has, so the name is but2ene. And in this, it has two sp3 hybridized carbon of CH3 and sp2 hybridized carbon of CH double bond CH. Actually, it gives rise to a restricted rotation. The free rotation is possible when carbon atoms are bonded through single bond, and the free rotation of carbon-carbon single bond gives rise to conformation analysis. Besides that, the restricted rotation of carbon-carbon double bond. Why it is restricted? See, it has a two bond. If it has only a sigma bond, you can easily rotate the molecule. But as it has a double bond, when you rotate one of the bond, the other will restrict to rotate the molecule, the rest of the one. So it is called restricted rotation. Then what are the conditions needed to exhibit geometrical isomerism? The doubly bonded carbon should have at least two different groups. If same groups are present, you can't able to exhibit that geometrical isomerism. See here, this sp2 carbon, it has one methyl and one hydrogen. This sp2 also has one methyl and one hydrogen. So the doubly bonded carbon can have two different groups of both the carbon atom, or the both of the two groups attached to doubly bonded carbon can be similar, or even two of them similar, and here the two of them may also be differ. So such molecules can only exhibit geometrical isomerism. So let us write how we are representing. See that in doubly bonded carbons, the similar atoms of hydrogen and similar methyl groups are of the same side. When such similar groups are of same side, that isomer is said to be the cis form of the geometrical isomer. And in this case, you are going to rotate this carbon-carbon double bond. So one of the group carbon atom having the groups alone be rotated. So the position of CH3 and H gets exchanged. So this gives rise to the transform of geometrical isomer. And in this case, the cis-2-butane is less stable. Why it is less stable? See, the bulky groups are of same site. So they feel or they have a great steric effect. Because of the steric effect, the molecule goes less stable. But in this case, the bulky groups are diagonally opposite to each other and the molecule is free from steric effect. So the transform of geometrical isomer is always more stable. Then, what about its dipole moment? This cis isomer has high dipole moment. What is called dipole moment is nothing but the product of charge separation and distance between the two charges, that gives dipole moment. In this case, when the molecules are differing in the air, electronegativity will show dipole moment. But in this, dipole moment will be less than the dipole moment of cis isomer. Because of the difference in dipole moment of cis and transform, they do differ in their physical properties. See, the one that may have a higher boiling point, melting point, the other one with less melting and boiling point. As their physical properties differ in their boiling point, we can able to isolate the cis form from the transform by either fractional distillation or gas chromatographic technique. Okay, let us explain how the doubly bonded carbon, it undergoes restricted rotation. See, this is what the representation of sp2 carbon. The sp2 carbon actually should have a double bond. So the one of the bond I said pi bond, one of the double bond I said pi, the other bond is sigma. The sigma bond is due to the head-on overlapping of carbon-carbon atom. So the pi bond is due to the side wave overlapping of p orbital. So this p orbital, both of the carbon, they have one electron in it. And you are going to rotate this carbon-carbon sigma bond. So what happened? The group will be twisted and hence CH3 goes above and hydrogen goes just below the plane. So you may find the difference in spatial arrangement of the groups attached to carbon-carbon double bond. So you can represent with respect to this methyl group, this is diagonally opposite. And you can represent this is the CH3 group. So in this the CH3 and CH3 are on same side, but the hydrogen are on same side. So with respect to plane, we can able to discuss about their relative position. This stereoisomerism is taken to conjugated diene system. What is called conjugated, you know? Conjugation means a single bond and a double bond in its alternate position. That is said to be a conjugate system. See that this is called 1,3 butadiene. 1, 2, 3, 4. The first position, third position, they have a double bond and there are 2 double bond. So the name of the compound is 1,3. 4 carbon are there. So buta. How many double bond is there? 2 double bond. Where are the position? 1,3 I given here. As it has a 2 double bond, I can represent butadiene. In this is the molecule. I can write CH double bond CH2, CH double bond CH2. See, same groups are of similar side, and the other groups are of another side. Such molecule is said to be cis 1,3 butadiene. And in this case, the rotation is about carbon-carbon single bond, not about carbon-carbon double bond, where in a conjugated system. And the same molecule, when you rotate, this is what happened. CH2 and H gets altered. So you will get CH2, CH, CH, CH2. Now CH2 groups are of opposite side. Such isomer is said to be trans isomer. That can be represented even in a bond line structure. See, in the bond line, this is the CH2 and this is what CH, this is CH2, this is CH. Similarly, it is CH2 group and other 2 carbon atoms are CH carbon. So conjugated diene system also exhibit geometrical isomerism. In geometrical isomerism, the other one is oximes and azo compounds. In the cis-trans isomerism, we have seen the restricted rotation about carbon-carbon double bond. But here we are going to find the rotation about carbon-nitrogen double bond. So let us take acetaldioxime. Acetaldioxime, actually acetaldehyde is CH3, CHO. When it is reacting with hydroxylamine, that gives acetaldioxime. CH double bond NOH. This is called acetaldioxime. So this molecule is taken over here. In this case, the nitrogen, it has unshared lone pair of electron. So one of the valency of nitrogen, actually nitrogen valency is 3. So you may find a double bond and a single bond about the nitrogen atom. So the valency of nitrogen is satisfied. Besides that, it has a pair of electron in its orbital. That is the orbital of 2s. Nitrogen, it has pair of electron in its 2s orbital. Besides that, when you rotate the carbon-nitrogen bond, we are going to rotate like that. What happens? The OH will go up above the plane and the lone pair electron goes to below the plane. So you may find the difference in position of the groups attached with the carbon and nitrogen. Carbon with the hydrogen, nitrogen with the OH that lie on same side. After the rotation of carbon-nitrogen double bond, then the OH and the lone pair electron gets altered their position, where you may find the hydrogen and the OH of nitrogen is just opposite to each other. When it gives rise to the 2 different structure, we have to say syn form and antiform. Syn form is nothing but the cis isomer and the antiform is nothing but trans isomer. So this form of isomer arises due to the rotation, restricted rotation about carbon-nitrogen double bond. Optical isomerism. The next part of stereoisomerism is optical isomerism. Some molecules, organic compounds, they have tendency to rotate the plane polarized light either in clockwise direction or in anti-clockwise direction. Such molecules are said to be optically active compound and the phenomena is known as optical isomerism. What is called plane polarized light? The monochromatic light, it travels in all the plane, in all the possible direction that it can travel. Such monochromatic light, when it is passed through nickel prism, it is restricted to rotate in a single plane. Such lights is known as plane polarized light. So, what are the conditions required for the compounds to exhibit optical isomerism? First thing, that carbon must be asymmetric carbon. What is known as asymmetric carbon? It should not have a plane of symmetry. Wherever you cut, it doesn't show the plane of symmetry. Such carbon is said to be asymmetric carbon. When will you get such asymmetric carbon? This is possible when the carbon valency, the 4, is satisfied by 4 different groups like this. See, this is the carbon. It has OH, COOH, H, CH3. So, this carbon, it has 4 different valency. But in this case, you may find CH3. 3 of the valency is satisfied by the hydrogen, but the 4th valency is satisfied by the rest of the group. So, this CH3 group cannot behave as asymmetric carbon, and COOH, it is actually C double bond OH. See, one of the valency is satisfied by a double bond and the rest of the valency is the group and other valency is OH. So, the doubly bonded will not take for asymmetric carbon. So, this lactic acid, out of 3 carbon atom, only 1 it has asymmetric carbon. So, such carbon, it is satisfied by 4 different group. That's why this carbon is said to be chiral carbon, and the compound has the property of chirality. Such compounds only able to rotate the plane polarized light. Okay, when the light is passed through the solution of lactic acid, depends on its nature that it can rotate the light to the clockwise direction. So, it gives a clockwise direction of rotation. Such clockwise rotation of plane polarized light by lactic acid is called D-isomer, or D means dextroisomer. Dextro means right side. And you are going to take the mirror image of this molecule. So, when you place a mirror just near to the molecule, you may find its image over here. So, we know when we look upon over the mirror, the top and the bottom will be similar, but the left and right will be just altered. Similarly, when this molecule is viewed by mirror, the top and bottom, the head and tail will be in their same position, but the molecules attached with sideway, that is left and right, gets altered. So, OH to the right side of the molecule, but in mirror image OH to the left side. Hydrogen to the left of the molecule, but in mirror image it shows right of the molecule. When I place this molecule over this, you are not supposed to place like this, you have to place like this. That means when we have the two hand, that is the palm, one over the other, you may find the thumb finger that overlaps with the little finger, and here little with thumb. Similarly, when you place this molecule over this, the H on OH and OH on H, that is said to be non-superimposability of the molecule. So, besides the two properties of asymmetric and chirality, the molecule whose molecule and its image should show the non-superimposability. Then only that molecule can exhibit optical isomerism. So, okay, the rotation of light, the molecule, the solution, if at all this have same concentration, the angle of rotation will be also equal. Suppose this molecule rotate the light to 80 degree and this molecule will also rotate the light to anti-clockwise direction of 80 degree, for which the concentration of solution will be same. So, when this molecule rotates its opposite direction, that is anti-clockwise, that is said to be levo rotation. Levo means left. So, or you can represent instead of dextro as plus, or levo by minus. So, the minus isomer is due to anti-clockwise rotation of plane polarized light by the molecule. So, depends on the rotation of plane polarized light, it gives rise to the two different form. One is D form and another one is L form. Such forms of the molecule is said to be enantiomer. So, in optical isomerism, we will get enantiomers which do differ only in the plane or rotation of plane polarized light, but they have same physical and chemical properties. This is optical isomerism. This is the topic from the next chapter of Samachir Kalvi, that is basic principles of organic chemistry. In that chapter they will discuss about the inductive effect, nucleophile, electrophile and all other things. Besides that, it explains about the different types of organic reactions also. We have different types of reactions: substitution reaction, addition reaction, elimination reaction, rearrangement reactions, etc. And all together can also take place, and besides that we have oxidation and reduction reactions too. Let us take first of all substitution reaction. Substitution reaction further classified into three types of substitution: nucleophilic substitution, electrophilic substitution and free radical substitution. What is called nucleophilic substitution? First of all, nucleophile, a group having a lone pair of electron or a negative charge. If I take CH3CH2Br, this is bromoethane, to which when it is hydrolyzed by aqueous NaOH, and this is also a nucleophile, this is also a nucleophile. This nucleophile is getting replaced by the OH group, where we are finding CH3CH2OH plus NaBr. So in nucleophilic substitution, one of the nucleophile from the substrate is replaced by the other nucleophile from the reagent. The next one is electrophilic substitution. It is usually carried out in aromatic compounds. So let us see benzene. Benzene that undergoes nucleophilic substitution of nitration. So this nitronium ion, or we can say even halogenation. Halogenation means it needs halonium ion, that is the halogen with positive charge we should take. This is halonium ion, and one of the hydrogen is replaced by this positively charged species. So we will get haloarenes, or it is halobenzene. Free radical substitution. In free radical substitution, let us take methane. This is when it is heated with chlorine in presence of sunlight. In presence of sunlight, the 4 hydrogen present in the carbon can easily be substituted by chlorine. So it can give CH3Cl plus HCl. See, all these reactions once again will be explained in detailed manner in the following chapters. So let us see only example for such types of reactions. The next type of organic reaction is addition reaction. Addition reaction also we have nucleophilic addition, electrophilic addition and free radical addition. And free radical we know a species with a dot, that is odd electron. Nucleophilic addition, this is usually possible. The addition reaction usually carried out in multiply bonded compounds. They should have a carbon-carbon multiple system, or carbon-oxygen, or even carbon-nitrogen. So where the multiple bonds, either a double or triple bond is present, there only the addition reaction is possible. So let us take the addition of CH2 double bond CH2 with HI. See, the I is nucleophile. So when it is added, I can get the compound of the type CH3CH2I. So after the addition of two groups to the adjacent carbon atom, the double bond is reduced to single bond. This is very important to note. And the addition reaction is just opposite to that of elimination. Here during addition you are finding double bond is getting into single bond. But in elimination, when these two groups are removed, then the single bond will be converted into double bond. So addition reaction is always opposite to that of elimination reaction. Then let us see electrophilic addition reaction. Here also I am going to take a doubly bonded ethene, and ethene molecule when it is added with bromine, first of all it forms an electrophile, that is our positively charged group will be formed, followed by the addition of other group. The mechanisms and all not required. The two bromine atom that shares with the two of the carbon, so we can have CH2Br, CH2Br. So this is 1,2 dibromoethane. And free radical addition. This is possible once again in ethane, where we are getting hydrogen chloride, and hydrogen chloride that breaks up into H dot and Cl dot, and these are highly reactive species. They can add to carbon-carbon double bond, so it forms CH3 CH2Cl. So in all the addition reactions, we may find the doubly bonded compound, that is the unsaturated system is into a saturated compounds. The next one, elimination reaction. Already I told you, elimination reaction is just opposite to that of addition reaction. And here, the elimination is possible, the removal of two groups from the adjacent carbon atom. The condition is elimination is possible from the adjacent carbon atom. See that this is the functional group bromine, which is attached to the carbon is called alpha carbon, and the successive carbon is beta carbon. So actually in IUPAC system we will designate the carbon into 1, 2, 3 etc. But in common system alpha beta notations given. So the functional group attached carbon is alpha carbon and the nearest carbon is beta carbon. So in this bromoethane or ethyl bromide, I have the halogen at the alpha carbon and 3 hydrogen at the beta carbon. When this ethyl bromide is treated with the alcoholic potassium hydroxide, the mixture is to be heated. Upon heating, the removal of halogen from alpha carbon and the removal of one hydrogen from the beta carbon takes place simultaneously, and hence the single bond of carbon-carbon that changes into double bond of carbon-carbon. How does it take place? See, I have taken CH2Br and the CH3, one of the hydrogen I just projected out. When it is heated with potassium hydroxide is an ionic compound, but it is taken in alcoholic medium. So this hydrogen, as the bromine is more electronegative, that withdraws the electron from the adjacent carbon, and it develops a partial positive charge over this carbon, and this partial positive charge that pulls another electron from the methyl group. So that is what the electron from carbon hydrogen. So it subsequently moves towards the alpha carbon. That's why this hydrogen that is left as a positive group and the halide that left as negative group. The negative group of Br minus adds with the K plus to form KBr, and the positive group of H plus that adds with the OH minus that forms water. So this is what elimination reaction, as the second group is being eliminated from beta carbon. This is also known as beta elimination reaction. And other name is also, it has a halogen and the hydrogen is removed. So this is also known as dehydrohalogenation. These are all just for information they have given in this chapter, but all these reactions will be discussed in detail in the following chapters. The next type of reactions, oxidation and reduction. Oxidation, it requires oxidizing agents. Those are either alkaline potassium permanganate or acidified potassium dichromate. Besides that, we have so many oxidizing agents. So these two are but considered as the strongest oxidizing agent. When it is taken to oxidize ethanol, it actually subsequently oxidized to aldehyde and carboxylic acid. So ethanol, first of all, on oxidation it gives acetaldehyde. Due to the strong nature of oxidizing agent, subsequently the aldehyde is converted into acetic acid. Reduction. Reduction in which the addition of hydrogen takes place. In the previous case, addition of oxygen takes place. In reduction, addition of hydrogen takes place. That can be done by taking the metal catalyst like platinum or nickel. We have other hydride catalysts also. So in which the benzene is taken when it is reduced by platinum or nickel, that provides space for to hold the hydrogen. That's only we are taking the metallic catalyst. So the 3 hydrogen that adds with the benzene ring, it is converted into cyclohexane, where C6H6 is converted into C6H12. So during the reduction, see that multiple 3 pi bonds are gets converted into nothing, the single bond only having. So the next reaction, functional group conversion. So let us take first of all alcohol. Alcohol, we have 2 types of alcohol, primary alcohol, secondary alcohol. Suppose if I have primary alcohol CH3, CH2, CH2OH, it is propanol. This is on oxidation with the potassium permanganate with the OH minus or potassium dichromate with the H plus or simply chromic oxide. So better I can take chromic oxide. This is an oxidation. Propanol is converted into propanol. CH3, CH2, CHO. See, this primary alcoholic group is getting oxidized into aldehyde. At the same time, if I take 2 propanol, this is 1 propanol. And if I take 2 propanol, that is CH3, CHOH, CH3, these 2 are isomer. When it is oxidized, you know, the CHOH is converted into C double bond O CH3. So oxidation of secondary alcohol gives ketone, but oxidation of primary alcohol gives aldehydes. So this is primary alcohol and this one is secondary alcohol. So primary secondary alcohol that can be converted into aldehydes or ketones by oxidation process. The other one is conversion of cyanides into amides or carboxylic acid. Let us take the compound RC triple bond N. This is called cyanide. When it is hydrolyzed by water in presence of acid, the CN group is converted into CONH2 group. This is called acid amide. When it is further hydrolyzed by water in presence of acid, then this bond gets broken. So we will get RCOOH plus NH3. See that? The cyanide upon partial hydrolysis, it gives amide, that is called CONH2. See triple bond N to which the water molecule is added. So a triple bond is converted into double bond with carbonyl group. On further oxidation, we can write HOH over here. So RCOOH, that makes carboxylic acid, NH2 with the hydrogen, that makes ammonia. So this is what the another functional group conversion in which cyanide is converted into carboxylic acid. The last one. Let us take an alkyl halide. This is depends on the reagent what I have taken. It may give rise to the 2 different kinds of products. See that? I have taken ethyl chloride with the aqueous NaOH, it gives alcohol. But with the alcoholic NaOH, this gives alkene. So in which the saturated compound is converted into unsaturated. So one of the functional group changes into other, and in this case the chloro compound is converted into alcohol. This is also one of the compound is converted into other. So in such a way one of the functional group that can be converted into other functional group. Okay children, all the topics from the 2 chapters of organic chemistry from Samachir Kalvi is completed. Hoping that you will understand all these concepts well. And let me include the link for the rest of the topic in the same site. Okay, thank you. Let us meet the next class. Until then, bye bye.